Geo RAS. In the case of HECHMS, we need to use HECHMS. But now the later versions and all, we have pre and post processor known as RAS mapper. So here the first thing is you should use the projection, set projection. So I already saved the projection file in a folder. So, okay. So this is the projection file. This you can download from one website. I will share you the website. Then create new RAS terrain. We have to create the terrain from the dump. So project, set projection. So this you have to apply and put OK. Okay. Then create new RAS terrain. You have to download the dump. So here we are using it for Manimala. We have already downloaded the Manimala dump. Okay, so create. So now it may take some time based on the dump and okay. So now dump is a terrain is created. So you can just see here. So if you click here, the elevation will be in above mean sea level. Okay, so this is some 625 like that. Elevation is above mean sea level. You can see here. So now terrain is created. Then you have to see the river network. So you can use map layers, right click, then create new RAS, add web imagery. So you can Google satellite image or Google map, etc. You can overlay here. Use Google satellite. So you can see the river network here. So I am selecting a small area, otherwise it will take long time. So okay, so this I will create a model for this small area. So the next is geometries. Then create new geometry. You can give a name. Just close it. Then edit geometry. So here you can add 2D flow. So I am going to develop the 2D model. So you have to select 2D flow area. Then perimeter. Select that. So then you can see a green color here. So you can draw the area. Then double click. Okay. Then you have to create the grid because this is based on 2D model is based on finite volume method. So here you have to select the spacing. Just I am giving us 100 meter by 100 meter. Then you have to also default value. You can give Manning's roughness coefficients. Here I am giving a 0.025. Then generate computation points. So you can see the number of cells only 36. Okay, okay, 36 only. Okay, so whenever you do the actual project, based on your problem area, you have to select the number of grids. And again, there will be issues like stability criteria in case of numerical methods. So you have to select based on the current number. Actually, you have to select delta x and delta y. Then compute table properties. Okay. So the number of grids are very small, so it will not be very accurate. Number of grids are less, so the model will not be very accurate. Just to demo, I am showing here. Then you have to give the boundary conditions. So here, boundary condition lines you have to specify here. Just to zoom in. So here you have to give the boundary condition, not condition, boundary lines. So this is, the flow is from here to here. So this is the upstream or downstream side. This is the, because the river is joining into the Vembanad Lake. So this is the joining portion. So this is the downstream side. So I am keeping it as DS. Sorry. So this is the upstream side. So I will put it as upstream. Okay, so you have to save this. Now geometry file is created. Save this. Okay, so now you can just open that, edit geometry data, open geometry data, you can see the geometry file. So this grid is created with nodes. Nodes are at the center. Okay. Okay, so here the project name and geometry is created. Then edit. So you have to give the flow details, unsteady flow data. So here you have to give the values for boundaries. Now we have created only the lines to identify what are the boundary conditions. So here upstream. So actually this flow hydrograph you have to take it from the hydrologic model. Okay, if usually people will give for a particular rainfall what is the corresponding outflow hydrograph. So now I am going to give an event for a particular rainfall event. This is the outflow. So yesterday you have seen how to develop hydrologic model. Usually that you have to get the output hydrograph from that and input here. Okay, so now I am giving a random values. So here you have to give the date. You can, I will give some specific date, 3rd June. The same convention you have to follow. 2020, okay. Start time 0. This is the initial stage condition, 3rd June 2020. Okay. So here you can put it as 0. Some arbitrary values I am giving, but you can import it from the hydrology model output. So you can paste it directly here or read from the DSS before simulation, means you can directly read from the hydrology model, the outflow hydrograph. So I am giving some random values. Then interpolate missing values. Okay, so this directly interpolate. Then you have to give the slope, energy gradient slope. This I am giving some, okay, small values. Okay, so this is the upstream boundary condition. Then you have to give the downstream boundary condition. This usually will be normal depth. So you have to give the friction slope. To compute the normal depth, you have to give the friction slope. So now both boundary conditions are over. Say unsteady flow data. Then you can run the model, unsteady flow analysis. So select geometry, unsteady flow, then flood mapping. You have to, so you have to give the starting time. Starting time 3rd June. End date. So while you enter the flow details, you should remember this starting date, ending date. Okay, so then compute. So complete the process. So you can now see the output. So all pre and post processing is in HECRAS. Sorry, RAS mapper. So the input, all output, you can input, giving the input, you can use RAS mapper, and visualizing the output, you can use the RAS mapper. So here you can see the depth, water surface elevation. So because the model is not so accurate, that is why it's giving some, no, this is the floodplain now. Not floodplain, the inundated area, okay? So that's all. So you can see various options how to give the, actually only one parameter here is the Manning's roughness coefficient. So that you have to vary to match with your, you can use satellite data to the historical flood inundation depth. You can compare with this one and then vary the Manning's roughness coefficient. The only one parameter here, not like the other hydrologic model. Here, Manning's roughness coefficient, you have to adjust and vary the flow depth. This is for 2D, and 1D we have already distributed the tutorial manual that you can just go through that. So yesterday I have mentioned, so whenever you digitize the central, in the case of 1D, you have to give the central line of the river. So you have to digitize from the upstream side to downstream side. That is one thing you have to remember. And when you put the cross section, so from the left, from the central line to, from the left, you have to start digitizing the cross section. Not digitizing, you have to give the cross section from the left to right. So that is that two things you have to remember, and the other things we have mentioned it in the lab manual. So you can just go through that and do the step by step procedure you can adopt. Okay, this. So is it okay? Okay, so the main thing is the outflow hydrograph. You have to take it from the hydrologic model. Okay, so that is the link here. So for whether it is continuous simulation or this I have done for very event, just for a particular event, means 1 month, no, the hydrograph, not 1 month, 2 to 3 days. So what is a hydrograph? So we have, for an event I have given now. So yesterday you have done for a continuous process, so that you can, that output you can put it here and do for continuous. Is it okay? Any doubt? Ah. Mm-hmm. Yeah, yeah, okay. Okay. Velocity direction is not shown here. Right? Depth, okay. So depth minus the the total depth minus the ground may be the water surface elevation. Okay. Okay, I think you can just practice by doing more problems. So very easy. 2D is very easy. So 1D, the procedure you can adopt from the lab manual. Okay. Mm. No, no, no. We cannot take the entire area. It will be some, no, it will take long time because it is a numerical method that is based on the discretization scheme and the time, you are adopted. Means we, hourly time interval, we need the depth. So in that case, it will take more time if you are giving the entire watershed. So always select some particular area and do the analysis. That you have to take it from the actual case studies. So you have to check the elevation and find out the energy slope and time vary. Yeah, that is what there is an option to view that as here. So you can visualize here actually. Here there is you can see the bar here. So here you can visualize for different time periods how it is changing. The flood inundation depth is changing. You can just visualize that. Mm. Cell count. Yeah, yeah, yeah. Yeah, yeah. Yeah. U delta X by delta. Yeah. Um, then this will be accurate, more accurate. But again, computation time will increase. But this is somewhat very, very wide spacing, so it is not accurate. So you can again only 36 cells. So you can again redefine the cells. Okay. Okay. Are we, no, the elevation data is taking from the DUM we provided. So DUM data is very important, but actually you have to pre-process it in QGIS or ArcGIS and put it all filling and all. You have to do it in the GIS software and import it here. I have not done all those things. That you have to do it. Because the DUM image is very important, and you can even give the actual field data for cross sections and all. That also you can put it here. Any doubt? Any other? So always better if we have LIDAR maps, no, that elevation details from LIDAR. If we import it here, things, the results will be more better. That is at only one parameter here, Riemanni's roughness coefficient, that you can give it for different regions and all. That options you have to check. So how to, because now I have given a default value based on that it is taking, but now you have to give for different regions what could be the Manni's roughness floodplain and the river boundaries, what about the Manni's roughness coefficient that you can give, and do the that you have to check your flood inundation depth from the simulation model and the actual from various satellite images. Then you can vary the Manni's roughness coefficient. So that is only one parameter here, Manni's roughness coefficient. That you have to check. Actually, in order to teach you, I learned because I don't have any previous experience. So you can see the options how to give for different zones and all. Is it okay? Any other? Okay.
And it's also a good idea to start with steady state flow. Just to learn, and system may not be confusing. Then cross section, 1D steady state flow if you want to learn that. Then defining cross sections and see the profile of water that's moving. And then for changing the third number or Manning's roughness, you can check whether or not the water is moving fast or slow. Those are the calculation techniques that you use. If the water is moving fast, that means the roughness is less. If the water is stagnant or slow, that means the roughness is high. So that roughness is always changing. So that's an most important parameter in this model. You want to fully understand how the flood water is moving from one cross section to the other cross section.
That is what the one-dimensional, you can do it yourself, very easy. So whatever I have mentioned, or the two things you have to remember, from upstream to downstream, you have to digitize the river central line, then you have to give the river boundary lines, then the floodplain boundary line, then give the cross sections. That is the main geometry here. Then give the boundary conditions, then run the model. Then Manning's roughness coefficient here again you have to give. Even you can see each cross section. As I mentioned yesterday, for different cross sections, it will be calculated. The water surface elevation will be calculated each cross sections. So you can even see what about the cross sections for each the cross section you have shown, you have drawn. Then even you can manually edit that, or you can import data from your field work and all.